In this tutorial, I'm going to be discussing some ideas for GLSL compute shaders in TouchDesigner. I'm going to be making use of the atomic counters and some feedback systems with particle position, velocity, and color. And I'm going to also talk about some ideas for optical flow design towards the end of the video. And this is a talks that you can use in your projects. I'd ask that you cite me and give me credit if you do use it. And the basis of this talk is that Particle's GPU is fast, but maybe it doesn't quite do all of the things that you might want it to. So what it's doing is we have a fixed size texture, and by the way, everyone should know that this is in the palette. So you click this palette button, you go to Tools and Particles GPU. I'll close the palette. So each of these particles might go out of bounds eventually, and then when it goes out of bounds or dies for some reason, then it just gets spawned at the top again. But kind of the weakness of this system is that it doesn't allow a more variable input number of particles. So you can't so easily be spawning, say, 10 particles one frame, but then you want to spawn 5,000 particles the next frame. So this is one advantage of a more compute shader approach and not such a simple parallel pixel shader approach to doing this kind of system. So the big overview of how this works is we have an ingestion system that is taking our velocity and it's limiting it to, say, 1,600 particles per frame. So we have an input image with many pixels, that's over 2 million pixels, and we're looking for candidates, and we're picking a maximum of 1,600 candidates randomly. And so that is done with a random operation that I'll explain later. And once we have those candidates, you may or may not be able to find 1,600 successfully in the image. But suppose you find whatever amount, then we have a feedback system in which 1 million particles can exist. And again, not all of the particles need to exist. If you're providing an image with low velocity, but you're thresholding it and you're looking to have only particles spawn with high velocity, then you won't fill up your buffer. So each of those two steps, one step is the filtering step, and so that's taking the input image and it's looking for 1,600. That uses an atomic shader, an atomic counter. And then the other thing is you have the texture buffer with up to 1,000 or up to 1 million particles, and that is also using atomic counters to keep track of how many particles have been added to the system. So I will cover both of those uses, and again, I'll try to talk more about the optical flow talks later in the video. And again, this is a SOP version that I have that I'm just not going to bother sharing, but you can see that it has upward of 20,000 points, but it's cooking really slowly on the CPU, 6 milliseconds, 10 milliseconds sometimes. So that's not great. And you can see, yeah, 13, 14, 15 milliseconds. So that's only 20,000 particles, but here we can easily go up to 2 million, 4 million, and higher depending on your GPU, and it's very light. This is showing mainly CPU cook time. I think the GPU cook time isn't maybe quite accurate, but it is very fast. So I will get started by showing you more of the custom parameters of how it works before the compute shader details. And so each particle has a life expectancy and a life variance, and so this is a random number is going to be selected between 0 and this number, and it's going to be added to the life. So you're not going to have a negative value that gets added to 1.3, for instance. There is a velocity threshold, so we have an input velocity to our system, but you might be looking for particles to spawn with only a certain high enough velocity. So this is the debug view of that velocity. So you can see that if I raise this up a lot, then fewer particles might be able to meet the thresholds for being part of the 1600 new particles that can spawn per frame. So I'll lower that down again. Also, there's an alpha filter toggle. So that means that this image could be chroma keyed or something like that. So pretend this were my chroma key, then I could, then not every pixel would have alpha. And so now if I wire this in as my color map, now if I enable alpha filter toggle, that means that if the pixel that it examines for being a candidate, if that pixel has a color of alpha of 0, then it's going to be ignored very quickly, and so it's going to drop out of being a potential candidate to meet the kind of pre-buffer of 1600 particles. This example doesn't use any kind of chroma keying, so I don't need those, and I'll disable it. Next, there's max speed. So you can see a good variation in the speed that's coming from the system, but if I lower the max speed, then you can see some nice kind of roundedness. And then there is also a velocity post multiply. So this is kind of slowing all of them down, their initial spawn speed. Momentum is kind of like drag. So 1 would be full momentum, no drag at all. Softness is the texture. So if I increase the softness, then that circle gets a lot fuzzier. And this is a really nice feature. So we're mapping speed to size of the particle. So the input domain, if the speed is 0, then the scale from the velocity will be 1, and the speed is 0.34, then the scale will be 1. And so now this debug toggle is showing me this input domain. So the particles that are moving 0.34 are showing up as this brighter yellow color, while the slower particles are showing up as that kind of red and magenta color. So now if I were to increase the scale, then that means that the particles that are moving fast, they're moving say 0.34, then they show up larger. And this could be the opposite too. You could actually have fast particles show up smaller. So those are some interesting effects. But this input domain from 0 to 0.34 gets mapped to 0 to 1. So this could be 0.1, for instance. This could be 0.2, but then the speed gets remapped to 0 to 1, and then that goes through a power function, and then the power function goes into the scale. So you might have a value like if say the speed is 0.15, then that's halfway between 0.1 and 0.2, so that would be 0.5. So then 0.5 to the power of 2 is a quarter, and so then you would be a quarter of the way in between 1 and 2, so then the scale would be 1.25, for example. The scale is just applied across the board to all of the particles. And then the debug toggle, I'll disable that, of course, and then background, you can add or remove the background from the render. So I'll go back to some more normal settings. So those are the custom parameters, and now I can talk more about the details of the compute shader and the 2 stages. So I'm not going to cover the code in too much detail. I just kind of want to give an overview of some of the ideas of using the atomic counter. So the first thing is the filter. So again, we have our input textures, and we're trying to just find 1600 particles, 1600 pixels among these images. And so a naive approach would be to visit all of the pixels in order, starting from the bottom row and moving left to right. That would be a bad idea because you would have a lot of correlation. You'd have a lot of blank particles in a row, or you'd have a lot of good particles in a row, and so overall a randomized approach is better. So the solution I came up with for that is to figure out our number of particles based on the input texture, and turn it into a ramp. So that's going from 0 to this number -1, the number of pixels -1, and just put that through a random sort. And then this very long chop is actually being loaded as a texture, a texture buffer on our compute filter. And so this is a fixed and a non-cooking reordering of all of the random pixels in this. So what our shader needs to do is it needs to start with a random offset into this texture buffer here, and it needs to find an integer describing the pixel, and it needs to check that pixel, and then if it finds that pixel, that's great. Then we want to paint it into our image, and if it doesn't find the pixel, then it needs to try the next one. So it needs to just do an offset of one index to the right, see what that identifier is, and then take that value that's in here and look it up based on its 2D coordinate. So these are single integers, but those can be remapped into I-vec2s, integer vec2s, to look up information in our input. And so when I was mentioning that the thread or this shader can look into this system, and it can see a particle, and it can say that the particle is not a valid candidate. That's based on both the velocity threshold and the alpha filter toggle. And so when it doesn't find a valid candidate, it can retry. It can move on to the next index, and that's what this filter retries is for. Or it can just give up, and it can let the next thread keep looking. And so if this value is very low, then the number of threads is determined based on our dispatch size. And so I've made it so that the dispatch size is the same as the number of pixels. So this is 40 by 40, that's 1600, and I've made it so that we have basically 1600 threads. And so if the max filter size was only 1, then each thread would look for a pixel, and if the pixel wasn't a valid candidate, then the thread would just end. It wouldn't make any additional attempts. And so you can see that this buffer of up to 1600 pixels isn't filling as well, because some of the threads are just, they're picking their random point in here, but they're not finding one, and so they die, and the particle doesn't successfully write a particle to the output. So I'm going to raise this again, and I just want to show that there are two important atomic counters here. So one is the particle count for the output, and the other one is the particle count for the input. So we're keeping track of two indices here, two integers through our atomic counter. So the first atomic counter is kind of what I was describing over here. So at the beginning of the shader operation, it's going to start at 0, and every time we call atomic counter increment p try count, this number is going to be incremented, but the number that it returns here is going to be the number before you incremented it. So you're actually going to call atomic counter increment on our variable titled here, and ID is going to be 0 for the very first thread. ID is going to be 0, but because you called this, it's actually going to increment it, but ID is 0 for your usage. And so we have a random offset. This number can be very large, and it's an integer actually, even though it kind of looks like a floating point. It's just going into scientific notation. And so we have our ID, and based on our D and our offset, we are doing a lookup into the texture buffer. That is the texture buffer here. And we're getting a pixel ID, and that's just an integer, but then we take our pixel ID and we remap it into the 2D coordinate space of our input textures, which happen to be 1920 by 1080. Basically we have this loop where we are trying for a maximum number of tries, and and if we find a successful pixel based on its velocity and optionally also its color alpha, then we will write it to our output. And this is where the second atomic counter comes in. So that second atomic counter is called Pcount. So you can see in my code here, I'm doing atomic counter increment Pcount. So that's going to be 0 for the very first thread. And so, pretend this is 0, then out ID is going to be 0, and we are going to take our out ID and we're going to remap it to the 2D space of our output texture, which happens to be 40 by 40. So the simple trick there is the same as the input. You just take an out ID and you do modulus the x coordinate of the output, and you also do divide by the x coordinate of the width of the output. And so the Pcount is the number of successfully written output particles. And that's how, the first thread is basically going to write here, or it's going to write none at all. And in that case, then this part of the code that increments Pcount will never be incremented. So, the first thread could fail and Pcount never got incremented. And so then maybe the second thread is going to succeed in finding a particle, and so then it's going to increment Pcount. You can definitely try different experiments with this. I've found that it works well. So for instance, you don't necessarily have to have a dispatch size like this. You could actually have a larger dispatch size, and you could probably have fewer max filter tries. I have mainly chosen this because I think it's easier to explain and because it still does work pretty well. You can mess with the numbers, and I haven't been disappointed with how it performs, so I'm just going for this simpler approach. So a kind of standard that I've been using in this system later is to output velocity, color, and position. So this is velocity, color, and position. And a really great trick to know in newer TouchDesigner is that you can, this is our top, we can enable it with clicking A on the keyboard or clicking this button and then go to view as points. And this is just so incredibly useful for debugging that you can take anything that is a texture and visualize it as points. So this is kind of showing the same information that you get from this threshold. Also, if I weren't to cook this, then it would save on the computation. But it's being shown up here, so that's why it's still cooking this debug thing. So the inputs to our feedback system, our particle system, are what I said earlier: velocity, color, and position. And then we also have the same things as feedback. Velocity, color, position. So these are the 1600 particles, but these are larger. These are the million or is that 100,000? This is actually, am I only doing 100,000? 1, 2, 3, 1, 2, 3. So that's actually only, I'm only doing 100,000 particles, but it's looking pretty nice. So these are being fed back into the velocity here. So this shader, it has kind of a similar strategy for Pcount. So Pcount here is trying to figure out how many particles have been successfully written to the output, and P new check count is looking for candidates within here so that you don't check the same candidate twice. But in this case, we can actually, and we do want to check the candidates in a specific order, starting at the lower left corner, going row by row, left to right, because we've guaranteed that the valid particles are at the bottom of the image. So we don't need to do a kind of randomization. But basically, the shader is doing a similar thing. It's even simpler. It's looking for, it's keeping track of the number of successful output particles and the the index of the checked input. Regarding the style of this shader, there is a particle, and the particle has a velocity that's only a vec3, a color which is a vec4, a position which is a vec3, and then it has two things related to life. One is the expected life, so it could be 1 second, and then another is the life elapsed. And so actually life expected could be 2 or 10 or any number, and life elapsed is starting at 0 and then over real world time being incremented by a small amount, say a 60th of a second every frame, until it meets the life expected value. So when I was talking about Pcount keeping track of particles that got written to the output, what's happening is the particle is being loaded from the feedback textures, and it's being checked for validity. It's being checked whether it's in bounds and whether its life elapsed is too large. So the shader is pretty well organized, I would say, compared to my previous versions of this project. And so we are looking for old particles primarily. So old particle is going to be looking for the feedback textures based on our thread ID. And then we are going to update the particle, say increment its time and also move its position. And then we're going to check the particle for validity. So is it not too old? And if it's not too old, then we will write it to the output buffer and we will terminate. But suppose it was too old, then maybe we do want to check a new candidate, a new particle here. So we're going to do load new particle. And so load new particle is a function that's going to look at these textures, and it's going to keep track using an atomic counter starting at the lower left, going row by row up to the top. And then if that particle is valid, the new particle, then it's going to save that new particle. And the new particle might be invalid because it might actually finish all of the valid particles and get a texture, get a pixel up here that is invalid. And so that's why we want to run save particle. That's why we want to run check particle even though it's a new particle. This system is pretty lightweight for just 100,000 particles, but it's not doing any, it's not doing O of n squared computation, so it's not doing kind of a flocking algorithm where you compare each particle's position to neighboring positions, for example. If I wanted to do that, I would do it in a separate shader. I would probably do it down here because I have all the positions here, and with all of these positions, then maybe I could have a shader with two outputs, and so this could go into a shader, and that shader could have an augmented velocity that would go here, and it could also have an augmented position that would wire into here. The purpose of this shader is not so much simulation, calculating new position or orientation or color or anything complicated. It's really just pruning. It's about figuring out which particles from the candidate texture should be added to the system, and then also figuring out which existing particles should be removed from the system because they're too old or they go out of bounds. And to think through some of the edge cases of this, the system is actually loading old particles in priority. So it's possible that your entire system could fill up, and if the system is full and the particles aren't too old or out of bounds, then it's not going to be able to look for new particles through this candidate texture, because again, it's just going to load old particles, and then it's going to update the particle, it's going to say it's valid, and then it's going to save it and return, and it's not going to add new particles. And so I think that is pretty kind of easy to understand, and also it's kind of easy to keep track of. You can see here in the position system, that it's filling up almost to the top most of the time actually. So I should probably lower the number of particles that could be added per frame. You could use math to figure out what these numbers could be more safely, so that overflow problem doesn't happen. But I think it's better to not be able to add particles to a system than to erroneously remove particles that are in mid-life cycle. So it's not such a bad solution. Let's see, and it's fast. So I think that we're doing everything in textures. Oh, the thing I wanted to say is that the particle has these fields. You'll notice that they're not all vec4s. It has life expected and it has life elapsed. I've decided to put the life expected in the alpha channel of the position, and I've decided to put the life elapsed in the alpha channel of the velocity. You may need to do something more custom to your system, but the reason I've chosen that is that TouchDesigner has recent additions of texture instancing, and this is a really great system, and it's probably the one of the main reasons I decided to just do this project from scratch again. I used to have a custom shader that would do the instancing based on these textures, but this new feature is so great that I really wanted to clean up and reorganize and just get everything in textures and do instancing in a more straightforward way. So what that method is we have the outputs here. They are velocity, color, and position. And I just do some extra stuff here, but you can see that the position is RGB from the position buffer, and the A is the life expected. And so as long as this is non-zero, as long as it's a positive number, then the particle is going to show up here. But for instance, I was pointing out that some of these particles occasionally go blank, then these particles up here won't be instanced, even though the full kind of rectangle has been dragged onto the instancing page here. So that's why I'm storing the life expected here. And then the velocity channel, I mentioned that the alpha is the elapsed life, and so that's a value that's 0 and slowly getting higher and higher. And so what we have to do is take that value, and we also have to get the position texture in here. And so if we have both our life elapsed divided by our life expected, then we have a percentage from 0 to 1. And so then that percentage is going into this scale. And you can adjust the curves here to get a different scale animation that suits your taste. This is where that debug velocity is happening, and so we can just very easily replace our texture that goes to our coloring. So again, the coloring, the scale, straightforward. It's just the green channel from this thing, and the color is easy again. It's RGBA from our null instance color over here. And the render is it's just got some basic anti-alias, and the let's see what else. Depth test is off. I will leave it to the community to do an implementation that does sorting. So you could actually keep track of the Z distance in this system, and then you can do a sort by Z using something like Bitonic merge sort, which is in my TouchDesigner shared repo, or you can look at the CUDA sort top by Vincent Jose, and those are really great solutions for efficiently using the GPU to sort particles based on some metrics such as Z distance. So that would fix some of the Z fighting issues that might occur in here. In my experience, it just kind of coincidentally doesn't look so terrible, so I haven't bothered to do it. But yeah, I'm just pointing out that because depth test is off, you might get some weirdness in alpha, but it's not the most burdensome thing to try to fix. So that is the guts of this compute shader system. I think I will discuss the optical flow aspect of this just a little bit. So this is an optical flow talks that I released a few years ago even, and I'm doing it just in 3 hierarchical levels. This is kind of in the literature, but I improvised a lot, and you are encouraged to just figure out what works best for you. But you can see that this is a low resolution, and it has its own flow scale. And this is a higher resolution, and it has a different flow scale. That's the magnitude of the flow that is being added into this composite top. So this is trying to get the big motions, and this is trying to get the finer details. And you can see that in the debug here. And you can see that this one that's looking for the big motion is it's painted his head as moving pretty well, but you can see that it's only painting the top of his head here, whereas in this one it's painting more of his head, so that's desirable. And so then that just gets scaled up to match the resolution, and you can see that his whole head is painted more consistently. And so doing it in a pyramid structure is advantageous, and I regret not pointing that out earlier in my first video about using this tox. Next, I'll just point out that the velocity thing that I was explaining here, where we have this toggle, that is similar to what is happening here. So I'm going to switch to the temporal thresholds. And so now you can see that when it thinks the velocity is as high as 2, then it's painting it this brighter color, and when the velocity is small, like 0, then it's painting it a darker color, closer to this purple magenta. And based on these, the speed, it gets remapped, and so when it gets remapped, that has to do with the feedback. So we have a feedback system in here, and it's kind of like a cross top. But the parameter of the crosstalk is actually depending on the speed velocity. So what this means is that I've chosen on this thing down here, I'm going to switch to temporal thresholds again. On this one, when the speed is low, the feedback is 0.5. So that means that we are doing a kind of crosstop in those regions that are slow values, and so it's sustaining the old value by 0.5. And if I raise this a lot, then we're sustaining the values more. And so now if I were to go to the velocity render of it, you can see that the image, the magnitude of the velocity is being sustained a lot more, because when the speed is low, that means it went to a high value, but then it became a low value. And so as it goes to the low value, we're driving up the sustain. We're holding on to the larger value longer. And so I was picking about a value of 0.5, but the flip side of that coin is that if the value is, if this value here is very high and you're holding on to the previous value by 90%, say, then you are missing the opportunity to pick up new values. And so that's the flip side of the coin, which is that when the velocity is large, say 2, then you're going to have the input of 0. And so you can pick different values of the cross levels based on the input velocity, and that's going to give you kind of more sustain or more attack in how the optical flow appears in the image here. So this takes a bit of experimentation. Probably start with just one and work your way up to multiple ones. And Let's see if I have anything else to conclude with. I would say that this doesn't, I would say that, let's see, I have a network layout mode, and I have an overview layout mode, and I don't have much of a GUI here at all, so you're definitely encouraged to make a GUI for this. And I have some other ideas for GLSL compute shaders to do in the future. Just to give you a clue, they kind of have to do with having threads write to specific locations in a larger output image. So you have an input image of particles, and then you have an output image that is kind of storing voxels in which those particles exist. And so you might have a huge space of voxels in which particles can exist, and you can write to any of them as occupied, and then when you do operations on those voxels, you can efficiently find new particles, efficiently find neighboring particles. And so that's great for kind of flocking systems and Voronoi stuff and other designs. If you have suggestions for other videos, and especially questions about this project, feel free to leave a comment or use the GitHub issues page to ask questions. I'm glad to try to help out. Thanks for watching. Bye.